just continue. Oh yeah, before that, just to help you with some things, if you need some like calculation, something like this, I've already prepared something for you here, because okay, just a recap lah. Okay, there's a chapter I think orbit description in 3D, where we are given, let's say we're given the state vectors R and V, vector R and vector V, the position vector and the velocity vector. All right, and then from those 6 information, 1 2 3 4 5 6, we are to find the 6 orbital elements. For example, A, E, I, small omega, big omega, and is theta supposed to be theta? Theta here, all right, cool. And true anomaly. So for example, from here you can do all these calculations here to get find it. So this is a spreadsheet that I've done to actually calculate that. Just a word of caution, yeah, if you're using Excel to compute, for example, your trigonometric functions, sine, cosine, spreadsheets, Excel, Google Sheets, they work in radians, yeah, so you have to actually convert whatever answer they give into into degree, sorry. Okay, so yeah, so this is something that I've done. I updated yesterday how to get information from these 6 numbers here. You can get the length of those vectors, angular momentum vector, scalar eccentricity, how to find it. I've already done it here. How to find orbital energy, semi-major axis. So there are the formulas are all there. Okay, I'm just going to let you view this document here. If you need to do your own, you can check this. You can check all this, the formula here, and then do it yourself. Because I don't think I want to change anything here. Okay, this is a case where when you are given position and velocity vectors and you need to find 6 classical orbital elements. Okay, now what if you have 6 classical orbital elements, AEI, small omega, big omega, theta, and you need to find R and V, those vectors. So if you click on this one here, all right, this is where your 6 orbital elements are the inputs. Okay, so let's say you have such and such numbers, those are in degree. I change it to radian here, and then do all the calculations here. Okay, rotation matrix, and fine. Okay, so what I will do is I will just share this with everyone. No, probably not, later on, I guess. Okay, yeah. YB, is that yours or did you change it from here?
I saw it.
Yeah, I actually did it so that you can do it yourself. So okay, so maybe you can start with it. I'll give this link later. Okay, all right, so that's a recap on if you're given R and V, how to find all the other parameters, and all the other orbital elements. And if you're given all the other orbital elements, how to find R and V, the inverse problem, the method is also given in the spreadsheet. Okay, enough recap, and I hope you have already received the chapters yesterday. So those are just rough our chapters, what have been done since week 1 until now. And today we are going to go into a new chapter called Orbital Perturbations. Yeah, so let me choose the right yeah, so now we call it all orbital perturbations. Now you need to understand the word perturb. Yeah, what we have done now so far, we have always considered the ideal situation. Ideal situation here means that, you know, all our orbit are ideal, mathematically ideal. That means if we have an orbit that is shaped and sized like this, okay, it has its own A, E, I, small omega, big omega, and let's say there's a, you know, spacecraft on an orbit. It has its true anomaly, and this is always changing. This is always changing, no worries. And we assume that AEI, small omega, big omega, it's not changing. So this is what we always assume. Remember? Because we know that angular momentum is conserved, and we assume that there is no external force acting on our orbit. But the truth is, okay, there are still in space small forces that act on our orbit. Small forces that kind of pushed our satellite a bit by bit. And the force is not really big, but although they are very usually, the perturbation forces are very small, but as they act over time, so they will change our orbit over time. So some of these things here might change a bit, you know, here, something like that. Okay, I'm not doing a good drawing here, but let me show you an example here. Okay, so
now
let me just go straight to this one here. You can see this let me go to YouTube. I think it's easier, it's clearer to see here. Okay, now you can see here three orbits: the red orbit, white orbit, and the green orbit. Yeah, and the yellow one is just the equatorial line. In actuality, our orbits are not really fixed in one place. It changes bit by bit over time. So if you notice, if you look carefully on those white and red orbits, I think those are clearer. You can see it changes little by little every period, if you notice that. Now this is kind of opposite of what we talk about when we talk about constants of motion. We talk about, you know, conservation of angular momentum of the orbit is conserved. We talk about the total mechanical energy is conserved. What happened here? Well, what happened here is because there is a slight force, small perturbation forces that are acting on our satellite. Okay, now you know, for example, you have seen this. You know, this is our two-body problem. You know. Okay. So this is no problem. This is an ideal situation where everything is just, you know, nice. We don't consider any external perturbation. We don't consider any external force acting on an orbit. But in actuality, you know, we might have some small forces acting on our satellite as well. And let's call these small forces small perturbation forces. Okay, that is acting on our satellite. Now, if you understand the word perturbation, means perturbation in Malay, for example, means usik. It pushes you a little bit. Perturb, kacau. You know, it just push a little bit. So, where can these forces come from? You know, perturbing force. Where can it come from? Well, one is actually it came from the gravity. It comes from the gravity of the sun and gravity of the moon. Although they are far away, but sometimes their gravitational attraction is pretty strong, it kind of disturbs our satellite a bit. So we call this a third body perturbation. This is the small forces. This is a small force that is caused by the gravitational pull of moon and our sun, that is pulling or pushing our satellite. Okay, so that's such a solar flare. Oh, solar flare is not solar flare. This is actually originated from the gravity pull of those two bodies themselves, moon and the sun. By right in two body problem, they should not influence the motion of our satellite, but they still provide small amount of force that is going to disturb or perturb our orbital element. We'll show you what it does later on. Okay, what's the magnitude. Secondly, you mentioned solar flare. Actually, solar radiation provide a perturbing forces also. It's a source of perturbing force, solar radiation, because the reason is, sun emits light like photons, and you can actually feel perturbation force from the solar radiation as well. Although it's not much, but over time, when these small forces are acting on your spacecraft, it will, change your orbital elements bit by bit. Okay, so usually solar radiation will affect satellites on higher orbits. So if you're on low Earth orbits, probably you don't need to worry about solar radiation that much. Does any other planets or galaxies traction force included too? Well, third body perturbation is very, very small. So only the two significant one is moon and the sun. Perturbation force from galaxies or even Jupiter, or even our closest neighboring planets, Mars or Venus, really, really small, I would say. So, but the most significant ones are the moon and the sun, and even that, I'll show you later, is very, very small. Okay, so that's the, and this one, the third one, sometimes when in space, let me show you here. In space, well, space is considered when your altitude is more than 100 kilometers. Even in space, there is still some air density present. Okay, at sea level, of course, right now what we are feeling is the air density is 1.2 to 5 kilogram per meter cube. Okay, as you go further and further up, the air density becomes lower and lower, decreasing. You might think that once you get in space, the air density will be zero, but it turns out no, there is still air density left, but it's very, very small. It peters out as you go further above. So some of our satellites are in this region, 400 to 800 kilometer, low Earth orbit, in this region. And these satellites, which are in orbits, LEO orbit of 400, 500, 800 kilometer altitude, will experience this air density, and they will experience what we call the atmospheric drag. Okay, atmospheric, yeah, actually there's still small amount of air density in space, and what they will do is over time they will drag your satellite down. Just to let me see if this is working or not. As expected, I have I have something to show you here. So let's see here. This is an orbit of the ISS, and the ISS's orbit is very low actually, and over time you see the radius kind of decreasing, and this is what we call orbital decay, and it is caused by the atmospheric drag. So this is a short animation showing atmospheric drag effect on the ISS. So if you want to go look at it yourself, I'll give you a link here. Will it make the satellite orbit in reverse as time goes by? No. You mean the atmospheric drag? No. One is, well, you need really big velocity change if you want to actually go make a satellite go in reverse. Just for example, yeah, if you have a low Earth orbit, let's say you have an orbit traveling in a circular orbit, a satellite traveling in a circular orbit 7 kilometers per second in one direction. So to actually make them go the other way, you need 14 kilometers per second of delta V. So that's a huge amount. So, well, it's not possible that it is going to get it reversed. But what's going to happen though, if you don't do anything, like this ISS here, if you don't do anything to that ISS, what it will do, what will happen is the ISS will just its orbit will decay and will come crashing on Earth over time. So that is how most of the satellites in low Earth orbit is gonna get disposed. Well, that's the plan anyway, to make sure it decays over time. Okay, so that's the third one. The fourth one, which is the most important and probably not very intuitive right now, is what we call is the oblateness of Earth. Okay, let me explain to you what this means. Okay, you know that our Earth is not really a perfect sphere, right? It's not a perfect sphere. It's like a squashed ball. Okay, it's not a perfect. Let me show you here. Okay, so there's about 20 something kilometer difference between the equatorial and the polar orbit. So it's not really a perfect sphere. It's more like a squashed, ball. If you imagine a basketball and you sit on it, that's how it's gonna look like. I mean, the ball. That's how it looks like. Now, since it's not really a perfect sphere, you can be rounding. No, the question was, can it make it go reverse? No, I think it's really hard to do that. Now back to this one here. Now, since our Earth is not really a perfect sphere, so at different points of Earth you might feel different. The gravitational acceleration is not uniform because, well, the Earth's shape is not uniform. Okay, so this oblateness of the Earth, and because you can see some satellite are traveling this way, okay, and this non-uniformness of the Earth's shape will provide some kind of perturbation, and it's very significant. We call this one J2 perturbation. We will learn about this J2 perturbation. Okay, so hopefully there are only four the main ones that we are going to look at today. Third, body perturbation, the small perturbing force that comes from the gravity pull of the moon and the sun. Secondly, solar radiation. Yes, the radiation exerts some pressure on our satellite as well. Atmospheric drag, a significant, actually a really significant perturbing force, and also oblateness of Earth, the one that is, I think, is going to be the core of what we're going to talk about in this chapter. What about impact from space debris? Well, that we don't call that perturbing forces anymore. I think that would be a catastrophe. That's just like a bullet hitting you. So even what we are dealing with is when the perturbing force is kind of, it's acting on the satellite constantly over time. Okay, I won't say constantly because that's not right, but it's what we are talking about here are small perturbing forces that are acting on our satellite over time. That means every second they will feel this perturbing forces. Okay, so 4 things. Let's start with, I promised you just now, I want to show you the actually amount of, the third body perturbation. Yeah, well, if it's really disturbed or perturbed our orbit, how much does it perturb? Okay, so you know that caused by moon, yeah, this is the gravitational exertion of the moon is kind of perturbing as well, it's disturbing. It will change our right ascension of ascending node. It will change the satellite's run angle, right ascension of ascending node, by this amount, 0.00338 divided by n times cosine inclination angle. So if you want to calculate how much your right ascending node is changing over day, so this is degree per day, is this amount. You need to know the inclination angle of your orbit. Oh, let me oops. You need to know the inclination angle of your orbit, and this is what we call a revolution per day, revolution of your orbit per day. So if you're in on a low Earth orbit, so probably around 14 or 15 per day. So if you have these two numbers, then you can kind of estimate the amount, how much your right ascension of ascending node angle is changing per day due to moon. Okay, so it's a small amount, but it's changing a bit. And also the perturbation from the moon can change can change your argument of perigee by, well, a small amount, but still I see significant. Okay, divided by n cosine I, and the unit is degree per day. All right, so for example, if you are example, yeah, just let's do an example here. So let's say your inclination of your orbit, make a simple one. The inclination of your orbit is 0. Okay, so 0.00154, cosine 0 is 1. All right, and let's say you are in an orbit, low Earth orbit. I would say in one day it will revolve around Earth about maybe 15 times. Okay, so you can see how much degree per day is changing. It's not that much, but it's quite significant. Okay, that's for the moon though. What the moon does is actually it perturb our right ascension of ascending node angle, and also the argument of perigee bit by bit per day by this amount, this formula. So let's look at the sun. What does the sun do? So you think that the sun will change our orbit more. So how much it will change our right ascension of ascending node? Okay, the formula can be given as this: 4, 5 sine squared of I, okay, divided everything by n. This is also, the unit is degree per day. Alright, and this is also just like the moon. Let's do it here, okay. That's like the moon, it will change by this much, okay. Sine squared I over n, and the unit is also degree per day. Small amount, but still it's going to change our right ascension of ascending node bit by bit, our argument of perigee bit by bit over time. Okay, let me just give you the formula here so you can try and imagine it. So let's stop, and if you have any question, if you don't, I will continue to another one. What do you guys think? Okay. Okay. Is everything going all right? Am I still online? I don't want the last time that to happen. Yeah. Okay. Okay. But which part in the textbook? Oh, it's not in the Curtis textbook. It's on. I'll let you know which book I got this from. Pepe the Frog. Okay. So what I've given you here, these four formulas, are just to show you how much our moon and sun is changing our orbital elements, changing our right ascension ascending node and also omega. Okay, and these are the formulas, but remember that these formulas is only it can only be used when it's a near circular orbit. Yeah. So if E is near 0, then you can use this. If you have some kind of orbit, parabolic, hyperbolic orbit, this formula will be not useful at all. Okay, even in high elliptic orbit, it won't be useful. Okay. So let's look at the other one next, solar radiation. How much does it change your, well, let's see if you have let's see what kind of force does it exert on you. So usually solar radiation will act when your orbital radius is more than 800 kilometer. So if it's less than 800 kilometer, then, well, solar radiation is too small, way too small, so it's negligible. But after 800 kilometer, you can kind of estimate what value it is. Okay, so solar radiation I would say the force, okay, relation, it's about, I want to make an approximation here. It's quite small. It's about 4.5 times 10 to the power of 6, and this whole thing 1.4. Wait, no, let me rewrite that. 1 plus r, where r is actually what we call a diffuse. R is for reflection factor. Okay, as a reflection factor, how reflective is your satellite. So it can range from 0. R ranges from 0 to 1. Okay, so if it's really fully absorbing satellite, R will be 0, and for a specular reflection, it will be 1. So it will range between 0 and 1, but as you can see, it's very, very small here. Okay. Oh, sorry, I missed the area. We need area as well. 4.5 minus 4.5 times 10 to the power minus 6 times 1 plus r, where r is the reflection factor, and a, where a is the cross sectional area of your spacecraft. Okay, you will actually relook back at this stuff when we are doing satellite technology later on. Okay. Oh, question from Lee: will the value for n changes? N, you mean the revolution per day? Well, if in this case the sun and the moon do not change our semi-major axis. It will only change right ascension, ascending node, and argument of perigee. Therefore, the value of n in this approximation will not change. So if it stays in, say, an orbit of altitude 600 kilometer, so you can calculate how many revolutions per day, and then that's your value for n. Okay. Mind you, though, that this the actual calculation for how much these perturbing forces is changing our orbital elements is very much complicated. Yeah, what I'm teaching you here is just the quick way of quantifying these perturbing forces. So all these formulas that I've given you so far are approximation. Okay, and the third one is also atmospheric drag is also an approximation. Okay, you need actually a deeper, more thorough analysis to actually calculate the actual to actually quantify the atmospheric drag and how much it changes our orbital elements. Okay, now in this case, atmospheric drag, it will change. Yes, it will change our one is it will change our semi-major axis. Okay, and it will also change our period. It will also change our velocity a bit. Okay, so this is due to atmospheric drag. I'm just going to do AD here, atmospheric drag. Okay, so as you know, probably have you taken aerodynamics? Yeah, so you are familiar with coefficient of drag. Yeah. Okay, so as you know, whenever we are discussing about drag, so there's always coefficient of drag. It's going to get involved. So how much our semi-major axis is going to change um, over time. Yeah, for example, so this one, I'm just going to give you the formula here so they can keep it somewhere. Okay, a row, and then semi-major axis, the initial one. Okay, so again, this is just an approximation of how much our what we call it the semi-major axis is changing every revolution. Okay, and for period, change by this amount, CD A over V. Okay, V, and V is about pi over M. Okay, and okay, so I'm just going to leave you with this formulas now, but we'll do some exercises tomorrow to show you how atmospheric drag is actually how can we quantify the amount of drag, the amount of changes to our semi-major axis, our period, and our velocity of our satellite due to atmospheric drag. Okay, but tomorrow test betul juga. So maybe next week lah kot. Okay, so the last one is the obliteness of the Earth. Oops. Obliteness of the Earth. Okay. Tomorrow Waisak Day tomorrow Waisak Day, so cuti ke? Betul, period tu over square root M ke? Mana period mana? No. Irfan, bukan. So this is actually an approximation to so it does, if you see first time, it doesn't really correlate with what we know about orbital period, the formula so far. Okay, so the the one that we've learned, orbital period, that one is actually derived from Newton's universal gravitational law. This one is usually derived from experimental values, some approximation calculation made over time. When you have lots of data, and then you can make your approximation. So this is not based on any physical law, but based on some assumptions that we make for the satellite. Okay, M tu apa doktor? M is the mass of the satellite. Okay, M is mass of satellite. Okay, rho is the air density at that point. A is of course the cross-sectional surface area, and C of D is of course the coefficient of drag. Okay, so the last one and the most important one, I will continue this tomorrow. This is the most significant one, obliteness of the Earth. Okay, now we usually call this using the name J2 perturbation. What is J2 actually? Okay, the short explanation is this: when you try to describe a sphere when it's not really a perfect sphere, you're gonna have what we call zonal harmonics. Okay, And the most important one for our application, for space mechanics application, astrodynamics, if you're a space engineer, we should look into J2 perturbation. There will be J3, J4, and so on and so forth, but usually we only look at the J2 perturbation. Okay, now J2 is actually the J2 is a number. Okay, so for different planet, you're gonna have different obliqueness. For example, Mercury and Venus, we assume that I think it's good enough to assume that the whole planet is really spherical. It's oblique. It's not oblique at all. Zero. Well, it's unfair to say not oblique at all. It's not unfair to say it's nearly spherical, but I would say the obliqueness is zero, and it has their J2 value. But let's not look at other planets. Look at our Earth. Okay, our J2 value, that means 1.08263. Okay. Times 10 to the 1 negative. So this is the value of J2. Okay. Now, why am I showing you this number here? It's because, okay, the obliqueness of the Earth, the non-uniformness of our Earth, actually will change two of our orbital elements. One is omega, and the other one is argument of perigee, by much. You'll see that this value here, we'll continue this later on in our next class, that the value of change, the rate of change of the Rahn angle and argument of perigee over time is huge, that due to this J2 perturbation. How huge it is? If you start an orbit in January, for example, okay, by June your orbit is already facing somewhere else. It's got nothing. It doesn't look at nothing like your orbit in January. So we will look at the formula later on, and from this also we will learn many new things. One is what we call the sun synchronous orbit, which is the sun, the orbit that can follow the sun. And another one, we will see a Molniya orbit. So these two orbit here, special types of orbit, will depends a lot on our analysis about J2 perturbation. Total all these effects satellite juga or everything. Well, for our cases, for our studies, we will look into satellites lah, because sometimes we need our satellite to be at a certain orbit, and we don't want it to wander around. We don't want it to change orbit over time. But due to these forces, then it changes over time. Then we need to make some corrections. Now, does it affect only our artificial satellites? No, it affects I would say all celestial bodies, asteroids and everything. Okay, so we'll continue this next week on what is actually sun synchronous orbit and Molniya orbit, and what is actually J2 perturbation. Okay. Yeah, sure, Shikit. Do we have orbit graveyard? It's just a direction, Shikin. It's just a direction where it's going. It's usually, if you're talking about the solar radiation, it's just the direction. And why is this negative? Is because atmospheric drag will reduce your semi-major axis. That means the drag will make your semi-major axis lower, lower, and lower, lower. It will decay. Okay, just like the video I showed you just now. So that's why it's negative. Same thing as period as well, but not at velocity. Can you see? It's not negative, it's plus. That means as the semi-major axis is going lower, velocity becomes higher, which is scary. Okay. Now to answer Kenneth, do we have orbit graveyard? Well, there's something we call graveyard orbit. Is when, okay, you have your, this is just that, you have your low Earth orbit region here. Okay, so this is pretty much your low Earth orbit region. Okay. Now, as you go further to, let's say, your geostationary orbit, which is about 42,000 kilometers away from the center of the Earth. Okay, that's quite far, 42,000 kilometers. Okay. Now, if you have a satellite in the low Earth orbit, then it's easy to get rid of the satellite. Once it's defunct, when it cannot be used anymore, it's easy, you know. You can actually let it decay to low Earth orbit and let the atmospheric drag it down back to Earth and crash on Earth. Okay. So I think if you're here, then you can still do probably some maneuver. You want to push, use your rocket to go low orbit, or you want to use some kind of drag sail. You gotta push it a bit and then let the atmospheric drag decay your orbit back to Earth. Okay. Now, what if you are here? Now this is too far to actually, you know, to be dragged by atmospheric drag back to Earth. It's too far. So some idea is this: if you have a satellite this far, then you're going to have to actually kick the orbit further up to this very far away orbit. This region, let me show you this region with the red, blue. Okay, so this region here, it's just way too far from Earth, this region. Okay, so because you cannot dispose this satellite using the atmospheric drag, so what you can do is you dispose this orbit to a higher orbit, and we call this orbit the graveyard orbit. It's where all the lonely, useless satellite orbit alone here without any purpose. Okay, and it's just going to get destroyed by whatever asteroid hitting them, whatever debris. So this is where they end their life. Who kicks a satellite? Saitama. No, it's Garu. Now, well, you can some satellites, they have some what we call the end of time maneuver, where at the end of time you will just push this satellite into this graveyard orbit. Okay, so yeah, that is called a graveyard orbit. It's useless satellite there. There are many ways of we can dispose of satellite. Let me just show you a video of how satellites is disposed. Satellite, yeah. Oh yeah, graveyard orbits. There you go. All satellites are forgotten. You can see that. And this is an example of how some satellite, where it decays their orbit and come back down to Earth, and it disintegrate mid-air. So that is not a meteor, yeah. That's a satellite. Actually, it breaks up once it it goes too fast. It interacts with the atmospheric drag. So Ray, are you in the graveyard orbit? Let me pull you back in the low Earth orbit. Is it dangerous? What is dangerous? This one? Well, yeah, it depends on the size of the satellite, though. If it's too big, then it's probably dangerous. But usually, um, will drop in middle of ocean or in the middle of desert somewhere. If it's too small, then it will be disintegrated by the atmosphere. Okay. Yeah, destruction is beautiful. Okay. All right. Just to let you know that officially we'll end our class now. It's been a 1 hour. So, but if you want to discuss and look and see what if you have any weird question about